I'm Harshita, and this is not the Fibonacci project you'd expect. The Fibonacci sequence has a basic rule, where the sum of the previous two numbers add up to the next term. It starts off with 1 and 1, which adds to 2, then 2 and 1, which adds to 3. Wait, but I promised you a project that you wouldn't expect, so let's just get to the good stuff. The sequence also has many theorems that are long and tedious to prove algebraically, just like the two that I worked on in my project last year. However, tiling domino tiles to prove them is much more efficient.
In order to tile, we will be using these faceless domino tiles. Since these won't have dots to signify any value, there will be no differentiation between individual tiles. The three tiles we will be using are as such. The leftmost one is going to be known as a singlet, which is simply a 1 by 1 unit tile. On the other hand, these two will be known as doublets, since they're made of two singlets and they will each be 2 by 1. The one in the center will be known as a vertical doublet because its base will be shorter than its height. On the other hand, the rightmost one will be known as a horizontal doublet because its base will be longer than its height.
Let's take a look at how to tile an n by 1 board that is n rows across and 1 column up using singlets and doublets. There will be no vertical doublets in this case since they can't proportionally fit onto the board. The solution will be denoted as capital F sub n. In order to tile this, let's say the last nth space is x. Now there are two possibilities for what can occupy x. In subcase 1, where a singlet occupies x, there will be n minus 1 spaces left. Thus the solution will be capital F sub n minus 1. In subcase 2, where a doublet occupies x, there will be n minus 2 spaces left. Thus the solution will be capital F sub n minus 2. Summing both of these possibilities, the solution for capital F sub n, which is the number of ways to tile an n by 1 board, will be equal to capital F sub n minus 1 plus capital F sub n minus 2, which is the Fibonacci rule. If tiling an n by 1 board led us to the Fibonacci sequence, could tiling an n by 2 board lead us to possibly a whole new sequence? The solution for this can be denoted as capital D sub n. If we conform to our previous method of determining the number of possibilities of tiling the last nth space, as I showed in my paper last year, there are 5 total subcases of tiling this board, which in turn led us to this full recursive novel D sub n solution that I derived last year, along with a whole D sub n sequence, which will be expanded upon later. For my project this year, I worked on deriving a new sequence and definition for tiling an n by 3 board that was n rows across and 3 columns up. The solution for this can be denoted as capital D sub n. If we conform to our previous method of determining all possibilities of what can occupy the nth column, 7 distinct shapes arise with separate subcases within each. The first 3 subcases have either 3 singlets in the nth column, 3 horizontal doublets, or a vertical doublet and a singlet. The solutions for these are t sub n minus 1, t sub n minus 2, and 2 times t sub n minus 1 since there are 2 possibilities for subcase 3. The next 4 subcases are collectively referred to as triplet buses, because they're variations of the buses seen when deriving the n by 2 board in my project last year, as well as briefly explained in my project this year. The first triplet bus has a horizontal doublet on either the top or the bottom, and 4 possibilities. The second triplet bus has a horizontal doublet in the middle with only one possibility. The third triplet bus has 2 horizontal doublets placed adjacent to each other either on the top or bottom of the nth column with 2 possibilities. And the fourth triplet bus has 2 horizontal doublets placed separately on the top and bottom with only 1 possibility. Thus, the first general solution for t sub n is equal to 3 times t sub n minus 1 plus t sub n minus 2 plus 4 times b1n plus b2n plus 2 times b3n plus b4n. As stated before, the solutions for each of these triplet buses involved separate bus subcases. For example, for the first triplet bus, there were 5 distinct bus subcases involving solutions with other bus shapes. For instance, in this subcase here, where there is a horizontal doublet and a singlet in the x space,
the second triplet bus can be seen with one less row, giving us the solution of B2 n minus 1. Adding all these subcases together, a full solution for the first triplet bus can be derived. Similarly, solutions for the second, third, and fourth triplet buses can be derived. Substituting in these solutions into our original T sub n formula, the full T sub n recursive definition can be derived, which is T sub n is equal to 3T n minus 1 plus 13T n minus 2 plus 8B1 n minus 1 plus 5B2 n minus 1 plus 4B3 n minus 1 plus B4 n minus 1. Using this recursive definition, the first few terms of the T sub n sequence can be derived as well. In the Fibonacci sequence, if one term is divided by the previous term, a ratio approximately 1.618 appears, which is known as the golden ratio. As the numbers grow further apart, the ratio seems to get increasingly precise to this algebraic expression of 1 plus square root of 5 over 2, or 1.618. If we take a look at our D of n sequence derived earlier for tiling an n by 2 board, dividing one term by the previous term gets us closer to this ratio, which is approximately 3.214. However, its significance has not yet been determined. Eigenvalues have previously been used to determine the significance of the Fibonacci golden ratio, where here, if you have A, which is a 2 by 2 matrix, and V, which is a non-vector, it's going to be equal to lambda, which is the eigenvalue, times V, which is a non-vector. If A is equal to 1, 1, 1, 0, and V is 1 plus square root of 5 over 2, 1, then lambda is equal to 1 plus square root of 5 over 2, which is the eigenvalue, which again is the golden ratio. A similar method can be used to determine the significance of our 3.214 ratio in my D of n sequence.
Thank you for listening to my presentation. If you have any further questions, feel free to contact me through my email and I would gladly answer. Bye!